Children, once again welcome to our physics class. Hope you all are fine over there. Today we are going to start our new chapter, thermal properties of matter. So let's get started with today's session. You might have noticed that you feel hotter on a sunny afternoon as compared to a windy night. This is because of the difference in temperatures. Temperature is very high in the afternoon as compared to night. This chapter basically gives us the information about thermal properties of matter, where we will study about the properties of different substances by virtue of heat or heat transfer. So first, let's discuss about the basic concepts of temperature and heat. As you know, temperature is defined as the measure of degree of hotness or coldness of a body. Example, a cup of hot soup or a scoop of ice cream. So we can determine if it is hot or cold by measuring its temperature. So temperature is defined as the measure of degree of hotness or coldness of a body. Then what is heat? Heat is a form of energy, and it is transferred between two or more systems or a system and its surroundings by virtue of temperature difference. For example, a cup of hot coffee can be considered as an object or system, and anything apart from this hot coffee is surroundings. So the heat will flow from one object to another as there is difference in temperature. So here you can see when a hot cup of coffee is kept open for a long period of time, after some time it will become a cold coffee. What could be the reason for that? So a cup of hot coffee can be considered as a system, and all the other space apart from this coffee and the cup can be considered as its surroundings. So when a hot cup of coffee is kept open for a long period of time, heat is transferred from the coffee to the surroundings until the temperature of both the surroundings and the system becomes equal. So after some time we will see this hot cup of coffee will become cold as there will be transfer of heat. SI unit of heat is joule, and some of the commonly used units of heat are calorie and kilocalorie. So the SI unit of heat is joule, and other commonly used units are calorie and kilocalorie. Okay. And what is the relation between joule and calorie? Just note down the relation. 1 calorie is 4.18 joule. 1 kilocalorie is 1000 calories. The SI unit of temperature is Kelvin, and some of the commonly used units are Fahrenheit and Celsius. Usually you will represent temperature in Celsius scale or Fahrenheit scale. Our normal body temperature, it is 37 degrees Celsius. Okay, so these SI unit of temperature is Kelvin, and the other commonly used units are Fahrenheit and Celsius. And always remember this conversion formula: 1 calorie is 4.18 joule, 1 kilocalorie is 1000 calories. Now what do you mean by the concept of absolute zero? Absolute zero is defined as minimum absolute temperature of an ideal gas. And you had already studied about ideal gas and its properties, also the ideal gas equation in your chemistry classes. And what is the ideal gas equation? It is PV equal to nRT. And you are familiar with this equation. So absolute zero is defined as the minimum absolute temperature of an ideal gas. And the absolute temperature, that means the minimum possible temperature of an ideal gas in Celsius scale, is given here. Its value is minus 273.15 degrees Celsius, and in the Kelvin scale the same temperature is 0. Hence this temperature is regarded as the absolute zero temperature. So this is the value of absolute zero temperature in Celsius scale. This temperature is absolute zero. And on Kelvin scale the same temperature is taken as 0 point. The absolute temperature for a gas can be obtained by extrapolating the pressure versus temperature graph as shown below. So we know that PV is equal to mu RT. So the pressure is directly proportional to temperature. If we plot the pressure versus temperature of an ideal gas, you will get a graph as shown in the figure. And here on the y-axis you will plot pressure, along the x-axis temperature is plotted, and this is the nature of the graph, a straight line. And when you extrapolate the straight line graph backwards like this on the temperature axis, the graph meets the axis, temperature axis at this point, right? And this point is considered as minus 273.15 degrees Celsius. That is our absolute zero temperature. So the absolute temperature for a gas can be obtained by extrapolating the pressure versus temperature graph as shown in this figure. Next, we can discuss about thermal expansion. So what do you mean by thermal expansion? Thermal expansion is the phenomenon of increase in dimensions of a body due to the increase in its temperature. The change in temperature of a body may change its length, area or volume. So the fractional change in dimension, that is, what is the fractional change? Fractional change is ratio of change in dimension to the original dimension. Okay, so that fractional change in dimension is proportional to the change in temperature. For example, suppose the original length of the body is L, and due to the increase in its temperature, its length has been increased by delta L. So now the new length is L plus delta L. Now, so what is the increase in temperature, increase in length due to the increase in temperature? Delta L is the increase in length due to the increase in its temperature. And what is the ratio of change in dimension to original dimension? So ratio of change in dimension by original dimension is delta L by L. And this is the fractional change in the dimension of length. And this fractional change will be always proportional to the change in temperature. So delta T is the change in temperature. So that is the property of thermal expansion. The fractional change in any dimension, let it be length, area or volume, will be proportional to the change in temperature. The corresponding proportionality constant is called coefficient of thermal expansion or thermal expansivity. So thermal expansion can be defined as the ratio of increase in dimension of a body to the increase in its temperature. So whenever temperature of an object increases, its dimensions, it may be length, area or volume, may increase. And this property or this phenomenon is known as thermal expansion. And there are three different types of thermal expansion. So let's discuss about the three different types of thermal expansion. So before going into the categories of thermal expansion, we can just go through the interesting examples of thermal expansion. See, the water is cold at the top of the lake because it expands and becomes less dense. Okay, so when this water freezes, it insulates the water below it from the outside, which means cold air is like a blanket. It is because of this property many fish can survive in the winter. So this is one of the example of thermal expansion. Then another example is, as soon as we turn on a hot water tap, the water comes very fast as water is still cold. But as soon as hot water starts coming, the flow of water becomes less, and in some cases it stops. This is because the hot water heats the metal valve inside the tap. So whenever the metal valve is heated, it will expand and it will block off the further flow of water. Okay. On the other side, when an object is cooled, it contracts. It is referred to as a negative thermal expansion. Okay. So when an object is heated, it expands. When the object is cooled, it contracts. It is referred as negative thermal expansion. Now, what are the different types of thermal expansion? First one is linear expansion. Linear expansion is expansion in length. Area expansion, expansion in area. Volume expansion, expansion in volume. So what is linear expansion? Linear expansion means expansion in length due to increase in temperature. And linear expansion means fractional change in length. How the length is changing with respect to original length. Coefficient of linear expansion is a parameter which tells us how the size of object changes with the change in temperature. It is defined as the degree of linear expansion divided by the change in temperature. So, I had already told you, whenever the dimension of a body changes, the fractional change in that dimension will be proportional to the change in temperature. So here fractional change in the dimension length can be denoted as delta L by L, and that is proportional to change in temperature delta T. To remove this proportionality symbol, we will add a constant, and that constant is alpha. Okay, so we can rewrite this equation like this: equal to delta L by L equal to alpha L. Alpha L means it is a constant, and that constant is known as coefficient of linear expansion into delta T. Now, if this L represents, it is a linear expansion. Alpha L is the coefficient of linear expansion, or it is also known as linear expansivity. Now, from this equation, what is alpha L? Therefore, alpha L is equal to delta L by L into delta T, isn't it? So, this is the coefficient of linear expansion. And what is the coefficient of linear expansion? Coefficient of linear expansion is the degree of linear expansion divided by change in temperature. So, here when you look at this ratio, this is the degree of linear expansion, and this degree of linear expansion divided by temperature delta T gives the coefficient of linear expansion. Okay, that's why this is the definition for linear expansion. It is defined as the degree of linear expansion divided by change in temperature. So you must remember the expression for linear expansion. Okay, so what is linear expansion? Delta L by L is equal to alpha L into delta T. Therefore, alpha L is equal to delta L by L into delta T. Now, another category of thermal expansion is area expansion. So, from the name itself you can guess, area expansion means there will be an increase in area. Okay, so suppose this is the initial size of the object, and when this object having area A is heated, the area of the object has been increased. Now let the object looks like this. So here the area of the object has been increased by delta A. So the new area of the object is A plus delta A. Okay, so what is the fractional change in area here? Fractional change in area can be considered as change in area by original area. That is the fractional change in area, delta A by A. And this fractional change in area will be proportional to delta T, that is the change in temperature. And this proportionality symbol can be removed by adding a constant, and that constant is alpha suffix A, that is area expansivity or coefficient of area expansion. So we will get delta A by A is equal to coefficient of area expansion into delta T. And from this, what is alpha A? Therefore, alpha is equal to delta A by A into delta T. Okay, so this is area expansivity or coefficient of area expansion. And in the case of area expansion, there will be an increase in both length and breadth. You know, length into breadth will be area. Okay, so area means there will be two dimensions. So whenever area of an object increases, there will be increase in the dimensions of length and breadth. So this is about area expansion. And as you know, the coefficient of area expansion is defined as degree of area expansion divided by change in temperature, that we had already discussed in the previous slide. So this means there is increase in area of an object with the change in temperature. Next is volume expansion. So you can assume or you can guess what is volume expansion. Yes, whenever the temperature increases, there will be an increase in volume of an object. So here also we can consider, see, delta V by V is the fractional change in volume, and this will be proportional to the change in temperature. And to remove this proportionality symbol, we will add a constant, and that constant is alpha V. Alpha V is the change in it is the coefficient of volume expansion or volume expansivity. So from this, alpha V is equal to delta V by V delta T. So delta V by V is the degree of volume expansion and delta T is the change in temperature. So alpha V is the coefficient of volume expansion or volume expansivity, and it is defined as the ratio of degree of volume expansion divided by change in temperature. Now, so we had studied three different types of coefficient of linear expansion, that is, one is alpha L, coefficient of linear expansion, alpha A, coefficient of area expansion, alpha V, coefficient of volume expansion. Okay, so there is a relationship between the coefficients of all these types of thermal expansion. So first relationship is alpha A is equal to 2 times alpha L. That means the coefficient of area expansion is equal to 2 times that of coefficient of linear expansion. So let's prove this relation. So for that, you need to consider a cube of length L. So consider a cube and its length is L. See, this is a cube and its length is L. L be the length of the cube. Now due to the increase in temperature, the length of the cube increases by delta L in all directions. So what will be the coefficient of linear expansion? Alpha L will be the coefficient of linear expansion, and we had already studied the expression for alpha L. Alpha L will be delta L by L into delta T, isn't it? Now what will be the increase in the area of the cube? Because the length of the cube is increased in all directions, so there will be increase in the area of the cube. So increase in the area of the cube is delta A, and it is obtained by final area minus initial area. Final area minus initial area. Final area minus initial area. Now, what is the final area? Final area is L square, that is the area of the cube is A square. So here A is the side of the cube, here side of the cube is L. So the final area is L plus delta L whole square, because finally the length of the cube has been increased by delta L. So the final area will be L plus delta L whole square minus initial area will be L square. And when you expand L plus delta L whole square using the identity A plus B whole square, and when you subtract, you will get another term. So here L square plus delta L square plus 2L delta L minus L square. So here minus L square plus L square will be cancelled, and neglect the term containing delta L only. So delta L square can be neglected because it is very small compared with the other term. So we will get delta A as 2L delta L. So delta A is equal to 2L delta L. Increase in area is 2L delta L. Now just write the expression for area expansivity. So what is alpha A? Alpha A is delta A by A into increase in temperature. Delta A by A into delta T. Now what is delta A? Delta A is 2L into delta L. Here we had already got this relation. Delta A is 2L delta L, and area, what is the initial area of the cube? It is L square, then delta T. Okay, now here we have L, here one L will cancel, and we are left with alpha A is equal to 2 times delta L by L into delta T, isn't it? Delta L by L into delta T. And what is this delta L by L? Here 2 will be the, what is this delta L by L delta T? Delta L by L delta T is alpha L. So you will get 2 times alpha L. So we have proved alpha A is equal to 2 times alpha L. So what we have done? We have just first we write the expression for alpha L, that is delta L by L into delta T. Now consider a cube of length L and heat the cube. So its length will increase in all sides. So the area of the cube will increase, and the increase in area is final area minus initial area. So what is final delta A? That is increase in area, that is 2L into delta L. Then write the expression for area expansivity. So it is delta A by A into delta T. Substitute for delta A and A. So delta A is dual delta L and A is L square, and cancel the like terms. So we are left with alpha is equal to 2 times delta L by L into delta T, that is 2 times alpha L. So this is the relationship between alpha A and alpha L. Similarly, you can prove the relationship between alpha V and alpha L. So similarly, we will get alpha V is equal to 3 times of alpha L. That you can do by yourself. Okay. Alpha V, that means volume expansivity, is 3 times linear expansivity. So children, with this I am concluding my session. Notes of the topic and YouTube video have been uploaded. Please go through it. We will meet in the next session. Till then, take care all of you. Stay home, stay safe. Thank you.